All right, welcome back to Module 2, Modeling Distributions of Data. So there's going to be two sections in this module. And we are going to start with section 2.1. Your learning objectives for today are you're going to measure position using percentiles, interpret cumulative relative frequency graphs, measure position using a z-score, transform data, and define and describe density curves. Measuring position, so percentiles. Percentiles are one way to describe the location of a value in a distribution. So you could see what percent of observation are less than it. So in a percentile, you're going to see how many values are less than it. So you're going to take number of values less divided by the total number of values. So here, Jenny earned a score of an 86 on her test. How did she perform relative to the rest of the class? So Jenny's score here was an 86. So how many scored below Jenny? So 21 scored below her. How many are there total? 25. So to find her percentile, you would take 21 divided by 25, and that shows that Jenny is in the 84th percentile. The interpretation of that means she scored better than 84% of her peers. All right, let's look at this. This SIN plot shows the number of wins for each of the 30 Major League Baseball teams in 2009. Find the percentiles for the Colorado Rockies, who won 92 games. So how many scored below 92? 24. How many are there total? 30. So what's this percentile? 80th. So 80% scored below the Colorado Rockies. So they didn't do too bad. What about the New York Yankees, who won 103 games? They're at the very top. Does this mean they're in the 100th percentile? Is it possible for 100% to score below the New York Yankees? Absolutely not, because the New York Yankees are included. So how many scored below would be 29 out of the 30. So they're actually the 97th percentile. Okay, what about the Kansas City Royals and the Cleveland Indians, who both won 65 games? Oh, our poor Royals. All right, so there are two different 65s. So you are always going to go with the lower one, okay? So how many scored below the lower one? 3. Out of how many total? 30. So they are in the 10th percentile. Go Royals! All right, cumulative relative frequency graphs. Say that 3 times fast. So a cumulative relative frequency graph displays the cumulative relative frequency of each class of a frequency distribution. So the age of the first 44 presidents when they were inaugurated. So here I can see that there were 2 between the ages of 40 and 44. And you can see all the way down between 65 to 69 of giving you 3. So what is their relative frequency? Well, for relative frequency, first you got to see how many there are total. Well, there's 44. So relative frequency would be 2 divided by 44. And you could keep going for the rest of the classes. Cumulative frequency is just adding up the 2 and then adding 7 to it to be 9, then adding 13 to it. So this would be your 7 plus 2 more. This would be your 9 plus 13 more. This would be your 22 plus 12 more, etc. You're just adding on from where you started. So cumulative relative frequency, you're going to do the same thing, but with the percents. And at the end, you should get your total 100%. Unless you have some round off error. All right, so if I wanted to kind of display that, the cumulative relative frequency, in a dot plot going on, sorry, in a line kind of plot. So here I'm going to go and plot where I started with. Okay, so I had 0 before. Then between 0 to 45, I was at 5%. Then my cumulative, again, I'm adding up, I'm now at 21%. Again, I'm going to add for my cumulative relative frequency to the 55. Now I'm at 51%. And you keep going all the way up, okay, until you get to the 100% for those classes. And just kind of make a little curve through them. So this is your cumulative relative frequency chart going on. So it says, was Barack Obama, who was inaugurated at the age of 47, unusually young? So let's see. 47 would fall about right, let's see, 45, 46, 47-ish, right? So was he pretty young? I would say so. It looks like he was around the 10th, 11th percentile from here. So that means only 11% were below him. Estimate and interpret the 65th percentile of the distribution. Well, this is where 70 would be, so 65 would be right here. So there's the 65th. Go straight over to your graph and straight down. And it looks like you're around 58. So the 65th percentile is an age of 58. So at the age of 58, 65% of the presidents were younger than 58. Here's a little bit easier to see. Mine weren't so straight. These are a little bit better when you use technology. All right. On your formula sheet, you can find your z-score. Your z-score is the statistic minus the mean divided by the standard deviation. So z-scores tell you how many standard deviations away from the mean a value is. If it's a positive z-score, it's above the mean. If it's a negative z-score, it's below the mean. So here it says Jenny earned a score of 86 on her test. The class mean is 80 and the standard deviation was 6.07. What is her standardized score? So what is her standardized score is what is her z-score? So what I want to do is take Jenny's actual score of 86 and subtract it from the mean and divide by the standard deviation. So her z-score is approximately 0.988. This means that she scored almost one standard deviation above the mean. So what is this kind of telling us? So I'm going to come back to that, and we're going to look at this empirical rule to help us explain it. So the empirical rule is something that states the standard deviations with normal data. So it says that 68% of the data are within one standard deviation of the mean. So here if I have this density curve with the mean in the middle, it says that 68% fall within one standard deviation. So if I add the mean plus one standard deviation and subtract one standard deviation, 68% is within there. 95% of the data lie within two standard deviations of the mean. And 99.7% of the data lie within three standard deviations of the mean. So if a data value going back to Ginny, falls 1 standard deviation above the mean. So kind of think about adding all of this plus that part, and how much is that below her? So about 84% of the data is going to fall below her. So she would be in the 84th percentile. That's pretty good. So here you can just kind of see the breakdown. If you're within, this is 68%, this is 95%, right? 99.7%, and you can kind of just see the breakdown of where the data would fall. This is very good to know. An inflection point, it's where the graph goes from concave down to concave up, is always within 1 standard deviation. So that's where my inflection points are always going to be. All right, so let's look at this. The scores for all high school seniors taking the verbal section of the Scholastic Aptitude Test in a particular year had a mean of 490 and a standard deviation of 100. The distribution of SAT scores is bell-shaped, so it's approximately normal. Question A, what percent of seniors scored between 390 and 590 on this SAT test? Question B, one student scored 795 on his test. How did the student do compared to the rest? And C, a rather exclusive university only admits students who are amongst the highest 16% scores on this test, which I'm sure you all are. What score would a student need on this test to be qualified for admittance into this university? All right, see what you can do here. You can pause me and see what you can do. So first off, let's just draw the little bell shape and kind of fill in where all the scores would be. So it says our mean is 490, so I'm going to put that here in the middle, and the standard deviation is 100. So I'm going to keep going out 100 each way as I kind of mark those. Okay? So question A wants to know how many were between 390 and 590. So that's just within 1 standard deviation, so that's about 68% from the empirical rule. B, what did B ask me again? One student scored 795. How is that? So 795 is way up here. Wow. Okay. So that score is really, really good. That means that he was in the top, 0.15% of all the kids taking it. He's awesome. Or she, of course. All right, C. Since about 68% of the scores are between 390 and 590, this leaves 32% of the scores outside of this interval. Since a bell-shaped curve is symmetric, one half of the scores, or 16%, are in either end of the distribution. The figure shows these percentages. So, a rather exclusive university only admits the students who are among the highest 16%. Where would that fall? You'd have to have a score of 590 or better. Sorry about that. All right, using z-scores for comparison. We can use z-scores to compare the position of individuals in different distributions. Ginny earned a score of 86 on her statistics test. The class mean was 80 and the standard deviation was 6.07. However, she scored an 82 on her chemistry test. She thought she did worse. But the chemistry scores had a fairly symmetric distribution with a mean of 76 and a standard deviation of 4. On which test did Ginny perform better relative to the rest of her class? So here, when you want to compare how she was doing, you can find the z-score. Now, in this case, we want a higher test score. So we want to find the larger z-score will be the better test relative to the class. Okay. Now, if we were talking about maybe how fast you want someone to be, if you want to be faster than them in a race, then you'd actually want to lower z-score there because you want to have a lower time. But in this case, we want a higher score. Okay, so let's find her z-score for each of these two tests, the statistics and the chemistry. So I take her score minus the mean divided by the standard deviation, and I got 0.99. When we did the chemistry score, the 82 minus the mean of 76 divided by the standard deviation of 4, we got a z-score of 1.5. So she actually did better on her chemistry test. She was 1.5 standard deviations away from the mean. So relatively, she did better on her chemistry test. Yay! She needs to work on her stats. All right, transforming data. The effects of adding or subtracting a constant. Okay, so if I want to add or subtract a constant to every single observation, so think I had this distribution of data, so at different values, and I just added everything on. So now I'm at A plus some constant, let's say like 5, B plus 5, C plus 5, right? What happens to that data? So I have something like this. I just shifted it over to the right. I added 5. Okay. How does that change anything? Well, my center is now changed to the positive, so I would change my center by just adding 5 to my center. What about the spread? So here, this guy over here had a spread of C minus A. Well, this spread would be C plus 5 minus A plus 5, which would be C minus A. So the spread would not change. All you did was shift it over, you didn't spread it out. So when you add or subtract, the center changes, the spread does not. Here you can kind of see with this data example what happened. All right, what if I multiply? Remember, multiplying by a fraction is kind of dividing. All right, so when I multiply everything, everything is going to change, except the general shape. So your center will change, your spread will change, because now if I had these values, A, B, and C, and I multiplied by 5, 5A, now 5B is a lot farther out, and 5C is a lot farther out. So you've multiplied them, you've kind of stretched them out. So now, this could have been C minus A for the spread. This would be 5C minus 5A. These are different values. So your center has changed by multiplying. Your spread has changed by multiplying by that same factor. You kind of think of it like that. But the general shape would not change. If it was skewed left, it will still stay skewed left. If it was symmetric, it will still stay symmetric. And again, here's an example so you can see what's going on. All right, so the density curve, we've kind of talked about drawing them over box plots and different things. Density curves are always above the x-axis, and they have an area of exactly 1. And that's because it's like 100% underneath it. A density curve describes the overall pattern of the distribution. So looking here, the overall pattern of this histogram for the whatever's going on can be described by a smooth curve drawn through the tops of the bars. This looks very symmetrical. Just a quick review of what we've talked about with mean, median, mode, of what happens to the density curves, what happens to these measures of the center when it's skewed left, skewed right, and symmetric. So again, quickly, what's skewed left? This one's left. Which one's symmetric? The middle. And which is skewed right? This guy over here. Remember my little tug-of-war? Alright, so density curves, they display the patterns. They have an area of 1. The median divides into 2 halves. The mean is the balancing point. This is all review of what we've kind of been talking about. So the median, again, divides it into halves, and the mean is the balancing point. That's kind of redundant. Sorry about that. Okay, so let's look at this density curve. This is uniform because it's straight across. So what is the probability that the random variable has a value between 0.4 and 0.7? Okay. So I want to go, these are supposed to be points, it's really hard to see. So here I want to go between 0.4 and 0.7. So what's the area of that in relation to the entire density curve? Well, what should the whole area under the density curve be? It should be 1. So let's check that. So if I take 8 times 0.125, that is a total area of 1. So what's the area going on in the red here between 0.4 and 0.7? Well, I would have to do 0.7 minus 0.4 times the height of 1.25. Oops. Times 0.125, and I got 0.0375. So, which one would be the best? B. You guys try this one. This is again, uniform density curve. Which is bigger on this density curve, the mean or the median? Remember, the mean gets pulled out by the skew a lot more than the median. So is this skewed right or skewed left? It is neither. Okay, this is symmetric. Even though it's uniform, it is symmetric. So they are the same. All right, so z-scores, they will always make the center have a mean of 0. And they will always make the spread or the standard deviation be 1. This is highly important. Mark this, highlight this. The way we can denote this is like this guy. It goes mean, standard deviation. Okay, we have a normal distribution. Okay, this is funny. Ms. O'Malley, in case you weren't thinking about grading our math tests on a curve, I've prepared some templates you might find handy. So he says, here's one where everybody fails except for me. So this is him right here. It's kind of funny. Here's one where almost everybody fails except for me. And here's one where the test is so hard, everybody quits except for me. Anyway, so I thought that was pretty cute for your density curves. Thought you might like that. All right. So here we've already talked about this mean, median stuff. Just always know the mean gets pulled more than the median with the skew. That's going to show up over and over again on the AP test as some kind of question. So, in summary, we've learned about percentiles, z-scores, cumulative relative frequency graphs, how to transform data, and density curves. And I will see you in 2.2.